Good morning and welcome back to the final two lectures of this program. In these two lectures we will be discussing some trace theorems. You have already seen trace theorems, so we will do little more on a trace theorem on that, because last time you have seen the trace map, but we will characterize its range space as well as its kernel space. So, trace theorem. So, what you have seen is that when you have a domain omega, and its boundary, then if you have u in general, if so the function is in an integrable space restricting such phase to a boundary which is a lower dimensional subspace is not possible in general. For example, if you know u is in L2 of omega, it is rather difficult and you need something else to restrict to that the boundary. Okay, so there are ways of doing it, how to restrict the boundary, but when u is in H1 of omega, the same trouble exists, but then in the trace theorem which I have already discussed, you have seen that how to restrict u to the boundary, and then you also seen that this u restricted to boundary will be L2 of d omega. Of course, L2 of d omega defined by imposing the surface measure on d omega. Okay. So, you have defined, it is not that L2 of omega functions are restricted to do, rather L2 of d omega considered as an independent vector space and define on d omega a surface measure, and with that you will introduce that, and then there is a way of defining u restricted to. So, today we want to see what is actually its range, but then to do that you need to know the fractional, need to know the fractional order Sobolev spaces, which we are not going to discuss in general, but we will do some fractional order Sobolev spaces. For example, you need to know how do you define Hs of d omega. Okay. In particular, we need to know, in our case at least we need to know what is H half of d omega. This is rather difficult and we will not do a general definition, we will not, that you can read from elsewhere, but for certain domains like an upper half domain, so we work with upper half domain. We work with upper half domain. So, let me give you, the thing is that when omega is a general domain, the fractional order Sobolev spaces are difficult to define, but then when the space is omega is Rn, you already seen this one via Fourier transform, then you can define Hs of Rn as the set of all tempered distributions such that 1 plus mod psi square whole power s by 2 f hat, because s by 2 f hat is in L2 of R, and this is defined for all S in R, you see. So, you can define all the Sobolev spaces for all S in R. Yeah, so we are going to use Rn plus whose boundary is Rn minus 1. So, on that Rn minus 1 you can define Hs spaces, and that is what we get. But when S is, there is immediate remark, when S is positive you can actually characterize this little more, because once f is positive you can actually Hs of Rn, you do not even have to go to tempered distributions, this will be in L2 of Rn. So, prove this one, L2 of Rn such that the same formula 1 plus mod psi square whole power s by 2 f hat is in L2. So, what is a small exercise actually you can show both these definitions are true equivalent. Okay. That means if you start with a Tambor distribution and if 1 plus mod psi square whole power s by 2 f hat is in L2, it trivially f hat is in L2, that will imply f is in L2. So, prove it as an exercise equivalent, you see. And in this case you also have the norm f in Hs in all this is general, f in Hs is nothing but norm of 1 plus mod psi square whole power s by 2 f hat is in L2. So, you see on Rn spaces you have a way of doing it. So, we are going to state the theorem in this setup first, and then using this you can actually define Hs of d omega, which I will not do it, but if I get the time permits I will write the trace theorem with the that. Okay. All right. So, let us write down the trace theorem. Trace theorem. Trace theorem. Let us see how far I can go in Rn plus. Okay. What is Rn plus? You will have, this is the upper half plane, this is your Rn plus, this we will write it as set of all x prime xn, okay, and that belongs to Rn minus 1 cross R plus. That means basically you are telling to say that xn is positive. So, the last component is positive, and so what is this boundary? So, this is Rn plus. So, the boundary is Grn plus, that is nothing but your x prime 0 with x prime in Rn minus 1. Okay. And this can be identified. So, we write both, this can be identified with Rn minus 1. So, your boundary is Rn minus 1. So, can define this advantage, can define okay, Hs of Rn minus 1. You see, what is that? Set of all that the Fourier transform in Rn minus 1. So, you have to take the Fourier transform in correct spaces. Okay. So, so keep this notation in mind. So, with this, so we may, this is my omega now. So, even if I use omega is Rn plus 1. So, the theorem is that there exists a continuous linear map which we denote by gamma naught. Okay. So, the gamma naught is a mapping. So, this is the first thing, this you already seen it. So, gamma naught is a mapping from H1 of Rn plus to the L2 of Rn minus. This is continuity in this, okay, which you already see even in the general case L2 of omega, and here you get L2 of t omega. The second part is gamma naught of V. If V is smooth, it is your is equal to V restricted to the boundary. Keep this in mind, this is always the boundary. This so it is my boundary basically. The gamma naught is of V is nothing, V restricted to the boundary if V is smooth. Okay. Smooth means in this case it depends on which one you are restricting, whether the function is restricting or its derivative is restricting. If the function is restricting, it is enough for example, V is in what do you say, C of Rn plus bar. So, you see, so if you have continuity up to the boundary, and then it is the same thing. These are all already you have seen essentially for any both first two cases. So, the third case, what is the image of or the range of gamma naught, or the image range of gamma naught, which we also denoted by gamma naught of H1 of Rn plus. Okay. This is nothing but your H half of Rn minus 1. Again I am telling Rn minus 1 is the boundary of Rn. And the fourth one, I do not know fourth one, I can bit delicate, all these are very delicate to prove the kernel of gamma naught, that is nothing but set of all V in H1 of Rn plus. Your trace is already that trace. This is called the trace, gamma naught is called the trace map. Okay. Gamma naught of V is equal to 0, okay, on that space, that is gamma naught of V, and this is nothing but your H1 naught of Rn plus. That means if your trace is 0, such functions can be approximated by d of Rn plus functions, not d of Rn function. You already know that every H1 of Rn plus can be approximated by drn functions, but H1 naught means you can have that support within Rn plus. For that you need the trace to be 0. Okay. The continuity or density tells you H1 of Rn plus can be approximated by continuous functions or drn functions. Okay. So, let me try to give a proof as much as possible. So, it is my attempt in the couple of both the lectures is to finish give a proof. Some proof I will give you, but then you may have to verify certain computations, because the proof by Fourier transform. So, this is even to check your strength of Fourier transform to do that. So, it is enough if you start with let V be in d of, careful when I am writing here whether it is d of Rn plus or d of Rn. This is I am taking V in Rn, the entire thing. So, when you take V in Rn and then restrict it to Rn plus, it can have, so the support can be something like this. So, if you restrict, it can have support here as well. Okay. That is the thing, it can have the support up to the boundary. Okay. So, such functions are dense in H1 of Rn plus. So, it is enough to prove for this case the estimate it is in L2 of Rn minus. So, first thing is that I am proving for, so and so as you see, so consider x prime 0 on the boundary. Okay. It is in boundary of Rn plus. Okay. And then I want to know this is the, if it is smooth. So, I am just defining the, once it is continuous you can define on the boundary point wise. So, V of x prime 0, V of x prime 0, I write it in the square form, does not matter. Okay, otherwise also you can do that. This will be 0 to infinity. This is standard trick, dn of, dn means the nth derivative. Okay, V of x prime xn dxn square dxn. Okay, that is it, because V has compact support, at infinity it does not contribute, and at 0 you, this is nothing but d by dxn. Okay, d by dx. So, this can be written as minus 2 integral 0 to infinity V x prime xn and dn of V x prime xn. Okay. Now, apply just a Minkowski inequality, you get with some constant, this is less than or equal to some constant into no V, just one, integral of 0 to infinity modulus of V square plus integral of 0 to infinity dn of V square, you can do that. And then now integrate with respect to x prime to get it norm of V in L2 of Rn minus. So, it shows that L2 is V restricted to is in L2 of R minus 1. So, this actually implies V is in L2 of Rn minus 1. So, this is less than or equal to constant into norm V. The right hand side is a norm in Rn plus. So, you see Xn is integrated only from 0 to infinity, but integrate with respect to x prime in Rn minus 1. You have to do it in Rn minus 1. So, this will be in Rn plus. Okay. And the above functions are these functions are functions are dense in H1 of Rn plus. So, you are starting with the drn functions restricted, and that you are already proved it is by density theorem. It is dense implies star is true implies this can be extended the yeah, maybe I will write it in. Implies the extension implies there exists extension gamma naught from, that is what it shows, gamma naught from, because that functions are dense. So, you can extend, these are continuous linear maps to do L2 of Rn minus, satisfying the condition 1 and 2. You see what is your condition 1 and 2? You see this is by definition, this is what now we proved. So, 1 and 2 are obvious, which you are, as I said, you are already seen it. So, this is your gamma naught memory. So, the gamma naught is an extension which you can do it, a continuity. Okay. So, now let me, so the proof of 3, this we will do it in 2 steps, difficult little computation, proof of 3. So, we have to prove 2 steps. You have to prove what is you want to prove, gamma naught of H1 naught Rn plus. Gamma naught I deliberately put it because there are other trace maps. You have to prove that H half of Rn minus 1. Okay. So, first we prove one inclusion. So, so the first part of 3(1). So, we prove gamma the inclusion gamma naught of H1 naught H1, oh no, sorry, there is no H1 naught here. H1 is contained in H half. So, let me give you some 2 notations. I am going to use Fourier transform. So, I will use notation, we use tilde Fourier transform in Rn minus 1, okay, and hat we use Fourier transform in Rn, okay, these 2. So, whenever so do not get confused with the tilde we used for extension. So, this is only for this particular proof of this lecture, couple of lectures, okay, otherwise tilde is generally used by that one. Okay. So, we define, so define the restriction. So, again we start with the drn function. So, always to prove that because of the density. Okay. So, and then by closeness density all you will get it, H half of Rn minus 1. So, V is in drn. So, you put W of x prime is equal to okay, V of x prime 0. Okay. So, for me the definition, the constants I have calculated, I used Fourier transform this one. If you are using any other notation, I did not put any constant anywhere. So, if you are used any other notation, please keep track of your constants. Okay. So, this way if you define your norm f will not be norm f hat, there will be 2 pi power minus n. This I keep on telling you. So, whenever you are using any definition, you accordingly use that one. If there are error, the technically the general theoretically there is no error except for a constant coming with you. You have to put that constant as mentioned in the beginning, this constant will be there somewhere. So, you have to follow that constant. Okay. So, I am going to apply Fourier transform, in Rn first. I am going to do both ways. Okay. I am going to apply the Fourier transform for V x prime xn, and then I put xn equal to 0. So, I do not want to write too many ways. So, this is equal to by so you will have some 2 pi power minus n. So, I will not be writing this constant, as I said, I will just put a dot, you keep track of the thing. Your Fourier transform is e power I x dot of psi v hat of psi d psi. Okay. So, what I am going to do is that I put xn equal to 0. So, let me not repeat this, but you do not do it, you write it another equation. So, I will put 0 here. So, there will be 0 here, that xn x1 psi 1 x2 psi 2, that xn will go. So, you will get x prime psi prime. Okay. So, you have x prime psi prime. So, this is same as with that constant. So, not keep off it. This will be in Rn minus 1, okay, and then e power, because that does not have your psi coordinate, because of xn 0 psi n coordinate vanished. So, I will write integral of v hat of psi d psi n. Okay. This is with the d psi n of d psi prime. So, you see you can write that. Now, I apply Fourier transform in Rn minus for W. I can directly get that one by applying Fourier transform, because what I will do. So, Vx prime 0 is same as by notation, that is why I put this notation Wx prime. So, this one by the Fourier transform, the constant, if you are using the constant 2 pi power minus n, there the constant will be 2 power minus n n minus 1, minus of n minus 1 minus n plus 1, all that constant you have to keep track of it. Okay. So, what you are doing? So, that one e power minus, oh, I am applying inverse Fourier transform. So, I do not have this minus here. So, I will not having any minus there, that is all. So, I will not have minus here. Okay. So, I will have e power I x prime psi prime into, now W, you have to apply the Fourier transform to W. Okay, W tilde. So, I am applying Fourier transform to this one. So, here the Fourier transform is applied directly at the n minus 1 variable. Now, the Fourier transform is there is uniqueness. Okay, you can, so you have represented two things in a Fourier transform mode. So, by uniqueness implies this is W tilde. So, you compare these two, okay, compare 1 and 2, you see, you will get it W tilde of psi prime is equal to some constant integral of V hat. So, you see, you take n dimensional Fourier transform, integrate, these are all nothing to do with the actually distribution theory. So, now what we have to show? We have to show that W tilde. So, to show that W tilde is in H half, to show that W tilde is in H half of Rn minus 1. That is by definition equivalent to showing 1 plus mod psi prime square, you see it is in Rn minus 1 of H half, you have to S by 2. So, you have 1 by 4 W tilde is in L2 of Rn minus 1. This is what you want to show it. So, we will do that integral of 1 plus mod psi prime square, okay, whole power half W tilde. I will skip small calculations here. So, please do the calculations and then you derive the constants properly. D psi prime, this is you want to show is finite basically. Okay. So, this is equal to, of course, there will be some constant. I will write here 1 plus mod psi prime square whole power half, and then I will write I use the W tilde definition, that is nothing but integral of V hat square. W tilde is integral of V hat. Okay. So, maybe if you want eventually put a constant, all that. So, I will do some multiplications. Okay. I will do some 1 plus mod psi square. This is extra multiplication, I am doing it because you know where the V belongs to. You will have V hat of psi. So, that is I am just substituting my V hat, previous definition, modulus of psi square whole power minus half, and this integration is only d psi n, keep it in mind, okay, d psi n, and then outside you will have an integration of psi prime. Now, here you can apply your Cauchy Schwarz because this into V hat is in H half. So, you can apply this square. If you take that square, that will be finite because that is in H1. So, what you will have get is that you need something more to there. So, you apply Cauchy because this is only in one direction so far. I will apply the Cauchy. This is in Rn minus 1, this is in Rn. So, what you will get here is 1 plus mod psi square into modulus of V hat psi square, okay. Maybe there may be some half here, you will have integral of, that is a separate quantity, 1 plus mod psi square, okay. Yeah, because minus 1 you will get it d psi n, this is an important thing. So, square, so there may be some kind of half here, there may be also a half square V hat of psi square, a square whole, yeah, there may be something half, right. Yeah, check this, all this some parameters, so to check it, and so now you combine this is Rn, okay. So, this is separate, this is independent of V, combine this with this, combine and evaluate this. This evaluation is easy because this is a typical tan inverse function, you see, this is 1 plus mod psi prime square psi n square d psi n, you see, this is interesting. So, you will get a term in terms of psi, this is 1 by a square plus b square, a square plus t d square dt, 1 by a square plus t square dt, that is something like tan inverse with some constants. So, that is a typical plus 2 calculation. You do that calculation, you get in terms of psi prime, in terms of psi prime. Okay. So, with all these there may not be half, that whatever calculations are there, you do the calculation. So, this will give you some number in terms of psi prime, combine that with this, combine that with that, and then combine these two things, everything you can combine. So, what you will get precisely is less than or equal to some constant, that constant you can calculate exactly your known V in H1 of Rn. square. Okay, so H1 of Rn plus, eventually you can do that one. So do this calculation and then applying just a Cauchy-Schwarz inequality and you will get that. That implies norm of V x prime 0. This is the H half norm, H half of Rn minus is less than or equal to constant into norm of V in H1. Okay. Okay. And now by density 3 follows. By density 3 1, okay, the first part follows. That means gamma naught of H1 is contained in H half, okay, on the appropriate domains. Okay, it's already 3:34. So I don't know. Yeah, so let's see. I will do maybe little extra time. It's a bit difficult. Now we have to prove the next step 3(2) to prove H half of Rn minus 1 is contained in H gamma naught of H1 of Rn plus. Okay. So what I will do, I will probably stop here. I don't think I will be able to finish everything, and so to start with V, some Hx prime. The idea is to do an extension. So you see H prime is given in H half of Rn minus 1. That means you have your domain here, you have something is, this is your Rn minus 1, this is your Xn positive. The thing is that it is given here and you have to do an extension, possibly you have to extend it to this domain, and so that it remains in H1 and it remains in H1 function. Okay. So its restriction is this one, gamma naught of V. That is what we want to do. So we will stop here and continue in the proof we will continue in the next lecture. Thank you.